Okay, so we're at part 3 of this lecture, and we're finally ready to introduce a couple of, I guess, more clever techniques for matching called capacitive and diode matching that are pretty easy to implement on a integrated circuit and very powerful as well. So far, the best thing that we have considered is probably what we call the series match, in which we placed a resistor in series with the generator resistance. That forced the generator resistance total to be equal to the transmission line. So that gave us a match in one direction. So we only got one reflection back and forth before the ping-ponging stopped. And that was certainly good, but the one lingering problem was we still had a little bit of extra power burn, which we wanted to get rid of. And I want to emphasize that even though that power burn was relatively small, if we have a component that flips to a digital 1 and stays there for a long time, then that's a lot of power that's constantly being burned. And if you think about it, we might be able to accept that for a short amount of time, but there's no reason to sustain that forever. We only need that for a little bit to stop the ringing, and then we can sort of remove that effect. And so the first trick that we're going to look at, which is capacitive matching, is going to leverage that fact that we don't need to sustain that, that system forever. We only need that matching for a little while until the ringing settles out. So let me just start out by drawing this circuit right here, right? And this is, we're going to take 5 ohms only. I'm not going to add a series match resistor. And then here's the transmission line. You're probably sick of me drawing these little diagrams, but such as this section, we got to do this a lot. And I'm going to start out here. Let's keep these numbers from before. Let's say this is 5 ohms. This is 1 volt. This is 50 ohms. And this is 2 kilo ohms. All right. Let me just start out with putting that resistor in here that had value of 51.3 ohms. All right, if I complete this right here, that is what we called parallel matching. And parallel matching was helpful. But what I just said earlier is that we actually don't need this 51.3 ohm resistor forever. We only need it for a little while we achieve this match, and to basically suppress the ringing, and then we can basically get rid of it. So what is a good trick we can use to basically get rid of this resistor after some amount of time? Right, and the trick to that is going to be adding a capacitor just like this. And if we do that, we have a scheme called capacitive matching. All right, so think about what a capacitor is. A capacitor is kind of like a resistor that varies in time, because a capacitor starts out as a short circuit, right? A capacitor does not allow you to instantaneously change voltage. You can put as much current as you want right away, but you can't change the voltage. You got to wait, right? So a capacitor starts out as a short circuit because it's refusing a voltage change. But if you wait long enough and you pump that current through it, the capacitor is going to build up the charge and therefore build up the voltage, and it's going to stop. It's going to take as much voltage away from everything else in order to shut down or shut off that current. So if we wait long enough, this capacitor becomes an open circuit. When the capacitor is an open circuit, we basically removed this entire branch of the matching. And that's a good thing because, again, we don't want to waste that 51.3 ohms burning power for a long time. So you can think about this capacitor as creating a temporary match that only lasts for a little while. Now, how long do we want it to last? So if we have this value C, then we would expect this resistor-capacitor combination to have a time constant of RC, right? This will be the time constant associated with this branch right here on the end. And so basically, if we wait a few RC time constants, the capacitor is going to become an open circuit and it's going to remove this part of the circuit. All right, so what that's going to help us do is, this is the pure ideal wave that we'd like. Right, in blue, this is ideal. All right, adding this branch, if we just have parallel matching, or if we have no matching at all, then we're expecting this to happen. Right? We're expecting a problem like this. This is unmatched. And once we add this capacitor matching, what will happen is we'll get something like this. The capacitor is going to sort of slow things down a little bit, right? And we're going to sort of smooth everything over. And so there will be some approaching of that value, but again, the capacitor is basically going to smooth out these variations because it doesn't like things changing quickly or doesn't like things changing instantaneously. It's going to blur together all those voltage changes. And so this is what we're going to get with capacitive matching. So positives and negatives. Positives, it gets rid of the ringing, and that's a good thing. And it did so without wasting power forever. Yeah, it's going to waste a little bit of extra power in this initial stage because it's activating this 51.3 ohm resistor, and that resistor is definitely burning unnecessary power. Once this capacitor becomes an open circuit and cuts away this 51.3, the current sort of steadies out, and we go back to that sort of low power case. So we reach the ideal, but only for a little while. But only after a little while. All right. The other downside is that we have limited our speed a little bit, right? So we had this nice brick wall clock cycle that came out of the source, but what we ended up with was a little more of a gradual transition there. And this could be, if this is 10 nanoseconds, that could be significant. So if we're not careful, this is going to limit our speed a little bit. But that's not necessarily a bad thing, because in reality, if you put a wave like this into a digital logic circuit, what it will do is it will rectify that. It will wait until the moment the voltage crosses a threshold that's probably halfway in between 0 and 1, then will flip very quickly. And so the output of the next logic circuit will basically reconstruct a nice, perfect brick wall anyways. And so we can accept this without having too much of a problem. So the speed loss is there. We can manage that. And it's not going to be so terrible. There is a little bit of delay that's associated with that, and that could be problematic, right? We've got a little bit of a delay because we had to wait for that voltage to ramp up before the digital logic caught it and flipped to a 1. But in many applications, that's an acceptable trade-off to make if it means that we get both good matching, suppress the ringing, and we get the benefits of low power as well. Then this is a pretty good strategy. All right. There's a fourth technique that I'm going to introduce, and that's called diode matching. Now, I'm not sure that you have covered diodes before. I'm not going to assume that you have, but the good news is a diode is pretty easy to understand. In particular, one called a Zener diode. So let me introduce this. Redraw this circuit. All right, here's 50 ohms. Here is 5 ohms. And on the load, there's our 2 kilo ohms. Okay, I'm going to introduce a device called a diode. If you haven't seen a diode, it looks like this in a circuit. And a diode is kind of like a one-way conductor of current, meaning it basically allows current in this direction. This is okay. But current in the other direction is not okay. Right? That will not be allowed. Right? This is gone. So that's kind of what a diode is. It's a one-way rectifier of current. Now, a Zener diode is a slightly different variation on that. And typically, we add these little notches on top to indicate that it's a Zener diode. A Zener diode basically acts the same way, except if you put a big enough voltage the other way, you can get some current the other way. So if the voltage is big, you can conduct some current in the opposite direction. And there's usually a very fixed and well-known breakdown voltage to what's called a Zener diode. Right, so this is a Zener diode. Let me just draw what the IV curve of that would look like. Right, so on the x-axis here is voltage, on the y-axis is current. For a regular diode, typically, if the voltage is negative, you get no current, no current, no current. Once you place a high enough voltage of, usually it's about 0.7 volts, or what's 1 p-n junction breakdown voltage, then all of a sudden you get lots of current. You get as much current as you need to avoid any more voltage building up there. So you can think of this as a short circuit for any voltage beyond something like 0.7 volts. All right, so that's a regular diode shown here. A Zener diode is very similar. It's got the same branch here. It's got the same branch there, but it's also going to break down on the other end. And this could be at minus 5.2 volts, for example. It will again become a short circuit and break down right there. And this again is called a Zener diode. All right, now let me try to draw this into the circuit. The Zener diode is basically, we're going to draw two of them. The first will appear like this. And it will connect in parallel to the load. And the second will go from the load right here up to the power rail, whatever your power rail is. All right, so if this is 1 volt, if your generator is 1 volt, your power rail is also going to be 1 volt. All right, so what this Zener diode does, this Zener diode is going to be set to have a breakdown voltage of approximately your power rail, maybe a little bit higher, right? So if your power rail is 1 volt, maybe you make it 1.2 volts, right? 1.1 volts, something that's pretty close. And so what this is going to do is, as soon as a voltage across this resistor on the load attempts to go too high, right? This diode right here is going to break down and short it out, right? So going back to the ringing basically looks like this. If we were not matched, what the Zener diode is going to do, let me draw that in black. All right, this is voltage in the load, which if we do nothing is going to look like this. All right, when we throw in this Zener diode, then this first Zener diode basically says, no, I'm not going to allow you to get past 1.2 volts. And so it saturates right there. Any extra current that's needed will flow through the diode in order to ensure that the voltage across the diode does not exceed 1.2. All right, and then on the other side, it's going to attempt to drop below about 0.8. And if it attempts to drop below 0.8, this upper diode will basically stop it from doing so, because this upper diode basically dictates that the voltage right here, VL, can't become less than 0.8. Otherwise, there will be a problem, right? So, and that's going to sort of stick it within this range. It's going to very much tamp down the ringing, and eventually this will settle out. So this is a pretty good technique. It's very easy to do. Diodes are very simple to build on integrated circuits or on circuit boards. It's just a PN junction if you're doing this in an integrated circuit. So it's particularly important for an integrated circuit. And there is a downside in that you do get a little bit of burn power in that diode briefly while you settle out, but it's not so severe, and it's usually an acceptable trade-off in order to reduce ringing to a manageable level, right? This does not eliminate ringing entirely, because we still let it get up to 1.2 and 0.8, but it's small enough that this doesn't actually detrimentally impact our circuit. So here you're starting to see there's a variety of techniques that we can use on digital circuits that can suppress this ringing and provide us with quality matches, even if the transmission line doesn't match the line of the load. And just to repeat, a lot of times when you're designing this, we don't have full control of these parameters, right? Because again, it's advantageous for power reasons. It's advantageous to decrease the generator resistance as much as we can. It's advantageous to increase the load resistance as much as we can. And the transmission line impedance, we're kind of at the mercy of geometry, right? We have certain ranges of trace widths that we can do, and we can have a certain separation between the trace and ground planes, but we don't have ultimate flexibility to pick any transmission line impedance that we want. And for that reason, these matching schemes are very important to allow us to capture voltages and reduce these ringing and detrimental impacts without having to force these values to be something that we don't want them to be.